Hello there, students. Welcome back to the wonderful world of physics. We're going to talk about work, so let's get into it. You've already learned about energy in the lab that you did last week. So you know about kinetic energy, which is 1/2 times mass times velocity squared. For example, this arrow being released by the archer has kinetic energy. It's basically the energy of motion. Anything in motion has kinetic energy. You also know about gravitational potential energy, which is given by the formula mass times gravity times height. And for example, this guy has gravitational potential energy because he's at the top of a staircase and he could potentially fall down. And this one's a little bit harder to understand, but the idea is, if this guy actually fell off this staircase, he would acquire speed, so he would get kinetic energy. And so where does that energy come from? Well, it started as potential energy. He has the potential to get another kind of energy. And so in that case, the gravitational potential energy of this guy standing at the top of a staircase then gets converted into kinetic energy if he actually falls off or jumps off or something like that. So that's why it's called potential energy, because it has the potential to be converted into another form of energy. And we've already talked about how energy can be transformed from one form to another. Here's an example of that. So you've got this cyclist. He's got kinetic energy as he's approaching the hill. Obviously, you need some speed to get to the top of a hill. Let's say, for example, that just as he reaches the top of the hill, he just barely has enough energy, and so he actually stops for a moment when he gets to the top of the hill. So he has no kinetic energy, but energy is not destroyed, and so he still has it. It's just now potential energy because he's at the top of a hill. So he has the potential to get it back when he goes back down, which is what happens, and he converts it back into kinetic energy, which is because of his motion. And so he actually doesn't change how much total energy he has throughout this scenario. He just converts it from one form into another. But the question is, how do objects acquire energy in the first place? It's not like we all just have the same amount of energy all the time for our whole lives. So how do we get it? How does this arrow get kinetic energy in the first place? How does this guy get potential energy in the first place? So this is where we talk about work. Work, the concept of work, is when someone or something acts on an object, giving it energy. In the archer example, the archer pulls back on the bow, and so the archer is actually doing work on the string of the bow. It's actually giving the string potential energy. It's actually a different kind of potential energy. It's not gravitational, but it's elastic potential energy. But it's still potential. It's still, you're holding this string back. You're waiting to release it. So it's got the potential to spring forward and then transfer energy to the arrow. So once you do release it, then yes, that's exactly what happens. It takes that energy, it converts it into kinetic energy, which is the movement, and it transfers that energy to the arrow. In the case of the guy on the staircase, he does work on himself because he's climbing the stairs. So he's doing work, and he's basically giving himself energy by climbing the stairs and by doing that work. So the technical definition of work is specifically mechanical work, is when a force is applied on an object, displacing the object in the direction of the force or a component of the force. We'll get into that idea of direction in more detail. So for example, here's a guy pushing a box, and he's applying a force towards the right, and the box is being displaced in the same direction towards the right. Excuse me. So you've got work being done because a force is being applied over the course of a certain distance. Here's a slightly different example. You've got a guy pulling on, let's say, a rope which is attached to a box, and the guy is pulling on an angle, but the box is not moving on that angle. It's sliding across the floor horizontally, and so you've got a force and a displacement in slightly different directions, but still roughly to the right. And then in this case, we've got, let me just go back. And so this guy is doing work on this box, even though the force and the displacement are not exactly in the same direction. In this case, we've got, so let's say this guy is walking towards the right. He's not he's not like throwing the box up or anything. He's just holding the box at the same level. So he's walking towards the right, holding the box. In this case, because gravity is trying to pull the box down, he's applying a force to the box upwards, which is counteracting gravity and keeping the box at the same level. And so the force being applied on the box is upward, but the direction of motion and the displacement of the box is to the right. I guess my left, your right, I think. And in this case, work is not being done on the box because the force and displacement are at right angles to each other. And so they're sort of like unrelated to each other. Okay, so when it comes to work, the larger force that's applied, the more work is done on the object. That's point number one. Point number two, if you keep applying the force over a longer distance, then more work is done. If you're pushing a box, if you just push it for a meter versus if you keep pushing it for 100 meters, then that takes more work. Obviously, that makes sense, right? And so here's the formula. It's work is equal to force times displacement. And these two statements, I think, are pretty obvious when you look at this formula. More force is applied, more work is done. Or more displacement, more work. So here's an example. How much mechanical work does a store manager do on a grocery cart if she applies a force with a magnitude of 25 newtons in the forward direction and displaces the cart 3.5 meters in the same direction? Okay, well, this is a pretty simple plug and play. Just take the numbers, put them into the equation. 25 is the force, 3.5 is the displacement, and you get 88. And now let me just talk about the unit for a second. This is written as Newton meters, because force is in newtons and displacement is in meters, obviously. But work is also measured in joules, and so Newton meters are equivalent to joules. You can prove this using dimensional analysis if you want. But remember, work is how objects acquire energy, so it makes sense that we measure them in joules because energy is measured in joules. So therefore, the store clerk does 88 joules of mechanical work on the shopping cart. Okay, going back to the previous slide, except for this X over here. More work is not don't X. Sorry about that. Okay, hang on, forget about this for a second. Actually, if the direction of the force is different from the direction of the displacement, like in this example of the guy pulling the box attached to the rope, actually, we have this more complicated formula. Work is equal to force times displacement times cos of theta, where theta is the angle between the force and the displacement. So you need to take that angle into account when the force and the displacement are not in the same direction. So just as a quick aside, if the force and displacement are in the same direction, well, in that case, the theta would be 0. What's cos of theta? You should know from trigonometry that it's 1. And so what does this formula turn into? Well, it just turns into force times displacement, which is the same formula we had before. So this simpler version of the formula is not wrong. It's just that it only works when the force and displacement are in the same direction as each other. And so you can use it in that case, but if that's not the case, then you have to use the more complicated version, which includes cos of theta. And here's an example of that. So calculate the mechanical work done by a custodian on a vacuum cleaner if the custodian exerts an applied force of 50 newtons on the vacuum hose, and the hose makes a 30-degree angle with the floor. The vacuum cleaner moves 3 meters to the right on a level flat surface. The system diagram for the problem is shown. So basically this guy is pushing down on this, what he's doing is he's sort of pulling on this part of the tube, and which is 30 degrees above the ground. And by pulling on it, he's going to move this whole, main body of the vacuum to the right. But obviously it's not going to be like moving upwards. It's just going to be sliding horizontally along the floor. So you have this angle between the force being applied and the displacement of the vacuum cleaner. And so given we know the theta is 30, we know the displacement is 3, we know the, I guess I messed this up. We also know the force is 50, so then you plug the numbers in, multiply them, and you should get 1.3 times 10 to the 2 joules, and that's it. Therefore, the custodian does 1.3 times 10 to the 2 joules of work on the hose. So remember, well, anyway, let me go to the summary. So here's the summary. Objects acquire energy when work is done on them, like the custodian is doing work on the vacuum, and so the vacuum is getting that energy from the work that is being done. Work and energy are both measured in joules, which makes sense, and just pay close attention to the direction of the force versus the direction of the displacement. Okay, and that is your quick summary of